Hello everyone, welcome to PyNet Labs. My name is Varun and I'm a CCI SP certified professional with 15 plus years of industry experience. In this video, we are going to discuss the upcoming customized course on MPLS, iOS XR and Service Provider Foundations. We will also discuss ISS protocol and demonstrate how it works in the lab. So let's get started with the course overview. This customized course on MPLS, iOS XR, and Service Provider Foundations will be of 30 hours in duration. This course helps participants learn and master service provider core technologies, including Cisco IOS XR, routing protocols like OSPF, ISIS, and BGP, MPLS, and services like L2 and L3 VPN, and MPLS traffic engineering. This course is recommended for professionals who are already working in the service provider domain and also for the aspiring SP network engineers. This course is a prerequisite for advanced technologies like segment routing. As a prerequisite, you should have good knowledge of basic networking concepts. Now, let's talk about the course outline. In this course, we will follow the 80% lab and 20% theory format. In the first section, we will have a look at the service provider architecture and the different components involved. In the second section, we will have a look at the Cisco IOS XR and its initial configuration. We will discuss how Cisco IOS XR is different from Cisco IOS. We will see the initial configuration and the two-stage commit process in IOS XR. In the third section, we will discuss how OSPF is implemented in iOS XR. That includes OSPF single area and OSPF multi-area designs. We will also see how OSPF is configured in iOS XR and some verification and troubleshooting commands. In the fourth section, we will see how ISIS is implemented in iOS XR. So anyone who is new to the service provider domain finds ISIS intimidating. So the purpose of this section is to remove that intimidation factor and make ISIS easy to understand. In this section, we will discuss how ISIS works, what are the different ISIS levels, the ISIS intra and inter-level routing. We will also see how ISIS is configured in iOS XR and some verification and troubleshooting tips. We will end this section by comparing how ISIS is different from OSPF. In the fifth and the final section, we will discuss MPLS. For anyone who is working in the service provider domain, it's critical to understand how MPLS works. We'll start this section with the introduction to MPLS. Then we will discuss the operations of LDP. We'll see how LDP allocates and distributes the label. Then we will have a look at how MPLS forwarding is done and what are the different forwarding structures used by MPLS like FIB, LFIB, LIB, and RIB. Then we'll see how MPLS is configured in iOS XR and some of the verification and troubleshooting commands. We'll also discuss a very important topic in service provider domain, and it's called as the unified MPLS architecture. Then we'll move to the services. We will start the services discussion with MPLS L3 VPN and the different components involved like VRF, MPBGP, route target, and route distinguisher. Once we have learned the basic L3 VPN, we will see what are the different inter-AS L3 VPN options available, like option A, option B, and option C. After completing the MPLS L3 VPN discussion, we will move to MPLS L2 VPN. So that will include the virtual private wire service and virtual private LAN service. The last part will focus on MPLS traffic engineering. We'll see why there is a need of MPLS traffic engineering, how the IGPs like OSPF and ISIs has been extended to carry the additional traffic engineering information. We'll also see what is the resource reservation protocol and how it helps in bandwidth reservation. In the lab, we'll see how MPLS-T is configured in iOS XR. We'll also see what are the different traffic steering techniques for MPLS traffic engineering. And in the end, we will see the MPLS-T fast reroute mechanism. We'll see how link protection and node protection is provided using MPLS-T FRR. Now let's move to the lab section. This is the list of the 8 labs where we will be spending 80% of our time. The lab 1 focuses on iOS XR initial configuration. In the lab 2, we will see OSPF multi-area configuration and verification. The lab 3 will focus on ISS configuration and verification in Cisco IOS XR. The lab 4, we will see MPLS LDP configuration and verification. The lab 5 will cover MPLS L3 VPN configuration and verification. The lab 6 will focus on MPLS L2 VPN configuration that includes virtual private wire service as well as virtual private LAN service in iOS XR. The lab 7 will focus on MPLS traffic engineering configuration and verification. And the lab 8 will focus on MPLS-TE fast reroute that includes link and node protection configuration and verification. An important thing to remember here is that we will cover BGP as a part of MPLS L3 VPN and L2 VPN sections because BGP is used as a control plane protocol for L3 VPN and for virtual private LAN service, BGP is also used as a control plane protocol for auto discovery and signaling. Now that we have discussed the course outline, let's discuss the ISIS routing protocol. ISIS is a link state routing protocol initially created for OSI networks. So OSI networks are the networks based on the OSI reference model. Not many people actually know that the International Organization for Standardization not just defined the OSI reference model, but they also develop protocols for certain layers. For example, the Connectionless Network Protocol or CLNP was developed for the network layer of the OSI reference model, and the original ISI specification was designed to carry routing information for CLNP. Later, the RFC 1195 specified how original ISIs for OSI networks can be extended to support IP routing, coining the term integrated ISIs. One of the major reasons the people who are familiar with OSPF find ISIs difficult is because of the different terminologies used by ISIs. So let's correlate the terminologies used in the OSI network versus the terminologies used in TCP/IP based networks. So system means a network node, an end system refers to a host, an intermediate system is a router, circuit refers to an interface, domain is an autonomous system, and network entity title is a router address in ISO format. SNPA, which stands for Subnetwork Point of Attachment, actually refers to a layer 2 MAC address when broadcast network is used. It actually refers to a virtual circuit when ATM or frame relay networks are used. But since those kind of networks are very rarely used, we can assume that SNPA means layer 2 MAC address. ISIS also defines a concept of routing level, which means that the scope of routing with respect to areas. Level 1 refers to intra-area routing, while Level 2 refers to inter-area routing. Even though the ISIS has been extended to support IP networks, it still uses the connectionless network protocol addressing for its internal operation, and that addressing is called as Network Service Access Point. ISIS uses the Network Service Access Point addressing to identify individual routers and their area membership. The original ISI specification defined a variable length NSAP address that ranges from 8 to 20 bytes. But the Cisco implementation fixes the size of the NSAP address to 10 bytes, with the first byte identifying the authority and format identifier, which is 49, which means that it is a locally administered or private address. The next two bytes identify the area address. The next 6 bytes identify the system ID, which uniquely identifies the router where this NSAP address is configured. And the last 1 byte identify the service that this address is referring to. When the last 1 byte or the ncell value is set to 0, the NSAP address is called as the network entity title. It means that this address identifies the router itself rather than identifying any particular service running on this device. Under normal operations, a router must have at least one network entity title address configured in order for ISIS to work correctly on that device. Now that we have understood the format of the NSAP address, let's see some examples of the network entity title addresses. Let's consider this simple topology with 6 routers. So router 1, router 2, and router 3 are member of area 1, while router 4, 5, and 6 are member of area 2. So let's focus on the network entity title address configured on router 4. 49.0002 identifies the area to which router R4 belongs. Then 0000.0000.0004 is the system ID of router R4, and the last two zeros identifies the service on the router R4, which is 0. It means that this address is referring to the router itself and not any service running on this router. Now let's discuss one of the most important topics in ISIS, that is the levels of routing in ISIS. Routing in ISIS has a concept of hierarchies or levels, depending on the network scope in which the routing is being performed. Level 1 routing refers to the routing between nodes in a single area of a domain. Level 2 routing refers to routing between nodes in different areas of a domain. An ISIS router can perform any one of the following three roles in the network. The first one is L1 only router. It means that the router is capable of doing intra-area routing. The second option is L2 only router. Means the router is capable of performing inter-area routing. And the third option is L1 L2 router, which is a default on Cisco devices. It means that the router is capable of doing L1 as well as L2 routing. Means the router is capable of doing both intra-area as well as inter-area routing. Let's consider a sample topology. This topology has three areas. Router 1, router 3, and router 2 belongs to area 1. Router 4, router 5, and router 6 belong to area 2. And router 7, router 8, and router 9 belong to area 3. Router 1, router 2, router 8, and router 9 are L1 routers. Router 3, router 7 are L1 L2 routers, and router 4, router 5, and router 6 are L2 routers. Now let's discuss the ISIS levels configured on the router and its impact on the adjacencies. ISIS routers operate on each routing level independently. For each routing level, be it level 1 or level 2, an ISIS router establishes separate adjacencies with its neighbors running on the same level and maintains a separate link state database. To understand this, let's consider a simple example with two routers. Router 1 is configured as L1 L2 and router 2 is also configured as L1 L2. Since both routers they are in the same area, they will form an L1 adjacency. And since both routers are L2 capable, they will form L2 adjacency. Both routers will maintain a separate database for L1 and a separate database for L2. Please note the following area requirements to form adjacency. Two L1 capable routers establish L1 adjacency only if they are members of the same area. Two L2 capable routers establish L2 adjacency irrespective of area membership. It means that the area ID does not need to match to form L2 adjacency. Now let's see how the ISIS levels configured on the router can impact the adjacencies. In the first example, there are two routers, router 1 and router 2. Both routers are L1 capable. In this case, they will form L1 adjacency because both belong to the same area 49.0001. In the second example, both routers are L1 capable but they belong to different areas. Router 1 belongs to 49.0001 while router 2 belongs to 49.0002. Hence, they will not form L1 adjacency because for forming L1 adjacency, both the routers must be in the same area. In the third example, router R1 is L1 only and router 2 is L1 L2. In this case, L2 adjacency cannot form because router R1 is not capable of L2 routing. Both routers will form L1 adjacency because both belong to the same area 49.0001. Here in the first example, router R1 is L1 only and router R2 is L2 only. So they will neither form L1 adjacency nor L2 adjacency. In the second example, both routers are L1 L2 capable and both routers belong to the same area. So they will form L1 adjacency as well as L2 adjacency. In the third example, both routers are L1 L2 capable but they are in different areas. Router R1 is in area 49.0001 and router R2 is in area 49.0002. So they cannot form L1 adjacency, but they will form L2 adjacency since to form L2 adjacency, routers do not need to be in the same area. Here, in the first example, router R1 is L1 L2 capable while router R2 is L2 capable. Here, they cannot form L1 adjacency because R2 is not L1 capable. But both routers will form L2 adjacency. In the second example, router R1 is L1 L2 capable, but router R2 is L2 capable. Router R2 belongs to a different area 49.0002, while router R1 belongs to 49.0001. Here, both routers will form L2 adjacency despite being in different areas. In the third and last example, router R1 is L2 capable and router R2 is also L2 capable, but they are in different areas. But still, both routers will form L2 adjacencies because the routers do not need to be in the same area to form L2 adjacency. This is the summary of all the examples that we discussed so far. The first column indicates the first neighbor's configured level, while the second column indicates the second neighbor's configured level, and the third column indicates the resulting adjacency. Another important topic in ISIS is the area design. Here, we will compare the area design in OSPF and area design in ISIS. On the left-hand side, you see an OSPF multi-area topology, and on the right-hand side, you see an ISIS multi-area topology. In case of OSPF, a router can be part of multiple areas by assigning interfaces to different areas. But in case of ISIS, in normal operations, an ISIS router can be part of only one area. If you look at the OSPF topology, router R4 has one interface in area 1 and another interface in area 0. But in case of ISIS topology, you can see that router R4 is completely part of area 2 and router R3 is completely part of area 1. The area boundary in case of OSPF is on the router, but in case of ISIS, the area boundary is on the link. In OSPF multi-area design, area 0 or backbone is mandatory. Each normal area is connected to the backbone area. But in case of ISIS, there is no single area designated as a backbone area like area 0 in OSPF. In OSPF, backbone is formed by the routers participating in area 0. In case of OSPF topology here, router R4, R5, and R6 form the backbone area 0 because they are participating in area 0. In case of ISIS, the backbone is formed by a continuous level 2 path. In case of this ISIS topology, router R3, R4, R6, and R7 form this continuous L2 path, thus forming the backbone for ISIS. In OSPF, the backbone cannot span across multiple areas, but in case of ISIS, backbone can span across multiple areas as shown above. If you look at the ISIS topology, you can see that the backbone spans across area 1, area 2, and area 3. But in case of OSPF topology, only area 0 is backbone. In OSPF, the communication between normal areas happen through the backbone area. But in case of ISIS, devices in different areas can communicate as long as there is an L2 part between those areas. Now let's talk about the metrics used in ISIS. Cisco ISIS implementation assigns all interfaces the default metric of 10 regardless of their bandwidth. It means that an 100 Mbps interface and 1 gig interface will have the same metric of 10. Contrary to OSPF implementation, Cisco IOS or Cisco IOS XR does not automatically recalculate an interface bandwidth into its ISIS metric. The original ISIS specification defined the link metric to be 6 bits wide, resulting in the range of 1 to 63, and the complete path metric as 10 bits wide, resulting in the range of 1 to 1023. It is called as narrow metrics. At the time ISIS was defined, these metric fits were considered adequate. Today's requirements, however, call for a much wider range of metrics. Therefore, in RFC 3784, now RFC 5305, a so-called wide metrics were introduced, allowing for a 24-bit width for the interface metric and a 32-bit width for the entire path metric. It is strongly recommended to use wide metrics whenever available and supported. However, all routers in an area must use the same type of metrics. Now let's talk about the packet types used in ISIS. ISIS defines four types of packets. The first one is Hello PDU. This type of PDU or packet is used to establish and maintain adjacencies. ISIS Hello or IIH enables the intermediate system to detect ISIS neighbors and form adjacencies. The function of Hello PDU in ISIS is similar to the Hello packet used in OSPF. The second packet type defined by ISIS is link state PDU or LSP. This is used to distribute link state information, and its function is similar to the link state update packet in OSPF. The third packet type is partial sequence number PDU or PSNP. This packet is used to acknowledge and request missing pieces of link state information. It is similar to link state request and link state acknowledgement packets in OSPF. The fourth packet type is complete sequence number PDU or CSNP. It is used to describe the complete list of LSPs in the link state database of a router, and its function is similar to database description packet in OSPF. Now that we know the different types of packets defined by ISIS, let's have a look at the different adjacency states used by ISIS. So ISIS is much simpler in terms of adjacency states than OSPF with its 8 states. In ISIS, there are only 3 possible adjacency states. The first is downstate. Downstate is the initial state in ISIS adjacency. No IIH or ISIS hellos have been received from the neighbor in this state. The second state is initializing or the init state. IIH or ISIS hellos have been received from the neighbor, but it is not certain that the neighbor is properly receiving this router's IIH. So, a router is in the init or initializing state when it cannot verify the two-way communication with the neighbor. The third and final state in ISIS adjacency formation is the upstate. In this state, the IIH or ISIS hellos have been received from the neighbor, and it is certain that the neighbor is properly receiving this router's IIH. You can use the show ISIS neighbors as shown here to verify its adjacency status with the neighbors. Now let's come to the configuration part of ISIS in iOS XR. The first step in configuring ISIS in iOS XR is to enable ISIS process on the router. And you can do that by using the router ISIS command. The second step is to configure the network entity title. You can optionally also change the IS type to level 1 or level 2 only. Remember that by default in iOS XR the IS type is level 1 2. The third step is to enable ISIs on the interfaces. Optionally, you can change the circuit type as well on the interfaces using the command circuit type either level 1, level 1 2 or level 2 only. After seeing how to configure ISIS protocol in Cisco IOS XR, let's see some of the verification commands that you can use to verify the ISIS operation. The first command is show ISIS interface brief. So you can use this command to verify the interfaces which are enabled under ISIS. The second command is show ISIS neighbors. You can use this command to verify the adjacency or neighborship status. The third command is show ISIS hostname. So this command will give you the mapping between the system ID and the dynamic hostname of the devices. The fourth command is show ISIS topology. So as its name suggests, you can use this command to see the ISIS topology information. One of the most important ISIS verification command is show ISIS database and its variants. You can use the show ISI's database command to list the content of its L1 link state database and L2 link state database. You can use the show ISI's database verbose to get more information about each LSP in the router's L1 link state database and its L2 link state database. Please pay attention to the attach, partition repair, and the overload bit flags as highlighted here in the red. We are going to discuss more about those flags in a minute. To see all the routes learned by ISI's protocol, you can use the show ISI's route command as shown here. In order to see entire ISI's related configuration options, you can use the show ISI's command. As discussed, now let's talk about the flags that we saw in the show ISI's database and its variant commands. The first flag is the ATT or the attached flag. The attached flag is especially relevant in case of inter-area routing. When an L1 L2 router performs its L2 SPF calculation and determines that it can reach other areas beside its own, it sets the attached flag in its L1 LSP. L1 only routers in the area can use any router whose attached bit is set in its L1 LSP to reach other areas. By default, there is no prefix propagation from level 2 into level 1, and that is the reason the L1 only routers have no knowledge about prefixes in other areas. So reaching prefixes in other areas can therefore be accomplished by means of the default route. L1 only routers automatically install a default route towards their nearest L1 L2 router whose attached bit is set into their routing table. L1 router from the available L2 routers advertising their attached bit set choose the closest one and inject default route towards that router into its routing table. Now if you consider the topology shown above, R1, who is an L1 router, installs a default route towards R2, although R2 does not advertise such route in its LSP. What R1 did was to look at other routers' LSPs and from the available routers advertising their attached bit set, choose the closest one and inject a default route towards that router into its routing table. If R2 loses its connection to R3, it clears the attached bit and floods the updated L1 LSP. That will cause R1 to remove the default route pointing towards R2 from its routing table. So we will learn more about this attached flag when we see the lab demonstration. The other two flags are partition repair and the overload bit flag. The P bit indicates whether the router is capable of an optional feature that allows healing a partition area over the L2 subdomain. So this functionality is similar to an OSPF virtual link. The partition repair function was never widely implemented, and Cisco routers do not support it. Hence, it is always set to 0. Now, let's talk about the overload bit. If a router's LSP has the O bit set, the SPF computation on other routers will ignore this router when computing shortest path to other routers and their networks. However, the SPF will still take the directly attached networks of this router into account because these continue to be reachable. The router will thus not be used as a transit router to other routers, but it will still be considered as a router usable to reach its own directly connected networks. The overload bit is a very useful feature when a router needs to be taken out of service for maintenance without causing major disruption to the network. Instead of simply shutting down the router, setting the O bit first will make other routers immediately recalculate their routing tables. computing alternate paths that do not traverse this router. Now let's start the lab demo of multi-area ISIs. In this lab demo, we are going to consider the given multi-area ISIS topology. So we have router R1, R4, and R7 configured as L1 only routers, while router R2, R3, R5, and R6 configured as L1, L2 routers. Router R1 and router R2 are member of Area 1. Router R3, R4, and router R5 are member of Area 2, and router R6 and R7 are member of Area 3. In the first step, we will configure ISIs on all 7 routers. So let's get started and configure ISIs. Let's verify the ISIS configuration on router 1. Now let's go to router R2 and configure ISIs. Let's verify the ISIS configuration on router R2. Now let's go to router R3 and configure ISIs. Let's verify the ISIS configuration. Now let's go to router R4 and configure ISIs. Let's verify configuration on router 4. Now let's go to router R5 and configure ISIs. Now we'll configure ISIs on the remaining two routers, router R6 and router R7. The next step is to verify the ISI's neighborship. In the next step, we will verify the link state database of each router. As you can see, the L1 LSP advertised by router R2 has its attached bit set. Now let's go to other routers and verify its link state database information. Since R2 is an L1 L2 router, it maintains two separate link state database, one for its L1 level and another for the L2 level. In the next step, we will verify the routing table of router R1 and router R7, which are level 1 only routers. As you can see, the routing table on router R1 has a default route installed, and it has reachability information about prefixes which are only in its area. It does not have any information about prefixes in other areas. Now let's go to router R7. Router R7 also has a default route pointing to router R6, which has advertised the attached bit in its L1 LSP. Router R7 has reachability information for prefixes only within its area. It has no idea about prefixes in other areas. In the next step, we will verify if router R1 can reach the loopback of router R7 using the default route. As you can see, router R1 is able to ping the loopback of R7 because of the default route installed on both the routers. Now let's see the path taken by router R1 to reach the loopback of router R7. So as you can see, router R1 takes the path router 1, 2, 3, 5, 6, and 7 to reach the loopback of router 7. In the next step, we will change the default behavior and propagate prefixes from L2 database to L1 database. Now let's do the same thing in router R6. After configuring the route leaking from L2 to L1, let's verify the routing table on router 1 now. As you can see, router R1's routing table now includes all the prefixes from other areas as well. Now let's go to router R7 and verify its routing table. As you can see, the routing table on router R7 now has entries to prefixes in other areas, and this happened because of the route leaking from the L2 database to L1 database on router 6. In this demo video, we have discussed only the basics about ISIs. The customized course on MPLS, iOS XR, and Service Provider Foundations will cover all the topics mentioned in the course outline in detail. I hope you like this video and I'm looking forward to see you all in the training. Thank you.